So now let's look at some more advanced usage of this cutting lemma. So here we have a more complicated problem. We want to count the number of points inside a triangle. Okay? Remember that the first step of the cutting lemma was to dualize things. Well, so let's try to dualize. But now the question is, what is the dual of a triangle? Well, here the dual of a triangle can be thought of as the following. So think of a triangle as made of 3 lines. Okay, my lines suck. Let's try again. So you have 3 lines, say L1, L2, and L3. So in this particular case, the set of points inside a triangle are those that are below L1, above, so below L1, above L2, and below L3. But I mean, I guess you could also have a triangle that looks like this. So you have L1, L2, L3. So here you can be, I guess this is the same. Okay, I guess it's the same. So or I guess you could have a triangle that looks like this. So here you could have below L1, above L2, and above L3. Okay. So in general, you get 3 lines, and then you have some above and below relationship with respect to each line. Okay, so when you dualize it, you get something like this. Okay, and again, exact situation might change, but given a fixed triangle or given a query triangle, you would know what is it that you want. So in this particular case, what I have is that I want the set of lines that pass below L1, below L3, but above L2. Okay, so we're given 3 points as well as a below or above orientation, and I'm interested in the set of lines that satisfy all of these orientations. Okay, so in this case, the only lines that satisfy all these cyan lines, for example, this line passes below L3, above L2, but it doesn't pass below L1, so therefore it doesn't count, and so on. So the only lines that count are the lines that satisfy all of these properties. Okay, this seems like a very complicated problem to solve, but it turns out that we could use this multi-level idea to solve this more complicated problem. Okay, so let's see how we can do this. As usual, we build a 1/r cutting for a large enough constant r. Remember how the way the cutting works, right? So you get a bunch of triangles, and you have a set of triangles. As you get a set of lines, some lines pass above, some lines pass below, and some lines intersect the triangle. Here, let's say since we want to handle L1, and L1 is interested in set of lines that pass below it, we take the set of lines that pass below this triangle and store it in a secondary data structure. And then we recurse on the set of lines that intersect the triangle. Okay? So what is the recursion for this data structure? Well, we have r² triangles. Inside every triangle, we have a recursion. So the size of the subproblem that we recurse on is n/r by the cutting lemma. But then for every triangle, so for every of the r² triangles, we do a secondary data structure on potentially n lines that pass below it. So that's the recursion formula. Again, similar the way we analyze the partition theorem, the secondary, if you can show that the secondary solution solves to 2 plus some epsilon thing, then this is the recursion that we get. Because here the trick here is that this one is this one here. So the recursion only happens on S1. So S2, we can just assume that's a fixed value, or it has been analyzed. So I can just replace S2 with this. Okay. And since r is a constant, r squared is also absorbed into the O notation. So it's just enough that S is analyzed to be n squared plus some epsilon 1. Okay. So we get this recursion. And again, in the exercise classes, we're going to solve that this recursion for some fixed epsilon 1 and some large enough constant r solves to this value, n squared plus epsilon 2. Okay. So what is the query time? So sorry, before going to how the secondary data structure looks like, let's look at the query time. So what is the secondary data structure? Okay, wait, let me go back here. What is the secondary data structure supposed to do? Right? Remember, for a triangle in my cutting, I have stored the lines that pass below it in a secondary data structure. So therefore, at the query time, I look at L1 bar. Remember that I'm interested in a set of lines that pass below L1, above L2, and below L3. Okay, so the lines that are below this triangle are already below L1. So therefore, the secondary data structure is only supposed to find the subset of these lines that are above L2 and below L3. So that's what the secondary data structure is supposed to do. So with that in mind, let's look at the query time. So the query time here is like this. So the query is like to find the triangle, some triangle that contains my L1. Using the secondary data structure, among the lines that are below this triangle, find those that are above L2 and L3. Since they are automatically guaranteed to be below L1, that subset is part of the output, so I output them. But then there are some lines that intersect this triangle, and some of them might be above L1 or below L1, so I just recurse onto them. So remember that this recursion here is with respect to the current, or this is the real recursion, whereas step 2 here is just using the secondary data structure. So this is using the secondary data structure. So therefore, when I write the query formula, or the recursive formula for the query, I get the following. Again, ignoring the part of the query that is just producing the output, is that I have a query that I want to answer on endpoints. I find one triangle, again this is r squared. I inspect all the triangles, I find which one contains my query. I recurse on that triangle, so that's already Q1 of n over r. Then I have one call to a secondary data structure, which is Q2. And this Q2 could potentially have n lines in it, because all the lines could potentially pass below my triangle. So again, assuming that, what does this query solve? So the query solves essentially this. So it depends on what is Q2 is. But if Q2 is logarithmic or polylogarithmic, then the query time is going to be polylogarithmic as well. So now let's look at what is Q2. So Q2 is supposed to find, given a bunch of lines, supposed to find the lines that pass above L2 and pass below L3. Okay, so how do we do this? Again, we rinse and repeat essentially. We build a cutting here. And so for every triangle in the cutting, we look at the lines pass above the cutting. We store in a ternary data structure that is supposed to answer essentially that portion of the query. And then we recurse on every triangle in the cutting. The query algorithm is exactly the same. We find the triangle that contains L2. Using the ternary data structure, we find among the lines that pass above this triangle, those that pass below L3. Okay, but that's the problem we have already solved earlier, so that was a warm-up problem we solved. And then we recurse on this triangle. So again, the query time becomes like this. Remember that finding the set of lines that pass below a point is what we have analyzed before, so that's already log n. So this Q3 is log n. So therefore this Q2 solves to log squared. So therefore Q1, which was the original query time, solves to log cube. So therefore we have found a data structure with n to the 2 plus some epsilon space that has log cube query time for counting the number of points inside a triangle, or reporting the number of reporting the set of points inside a triangle.